Now, this is an IT conference, but the next talk, it sounds like it's a biology-related crime story because it's going to be about slaying bugs. And the person talking about slaying bugs is Julio Fort. He is a Brazilian-born, Poland-based information security engineer. He currently works as Director of Professional Services at Blaze Information Security, which is a company providing specialist cybersecurity services. He holds a master's degree in information security from the University of London. He started working in information security after he realized that he could actually get paid for things that he used to do for free, which is basically hacking other people's computers. On top of that, he realized that maybe doing time in jail wasn't that much fun, so he switched to doing all that legally. And Julio will be talking to us about slaying bugs and improving software security through fuzz testing. Let's give him a warm welcome, Julio Fort.
Hi, everybody. Thank you very much for coming to the talk. Holy shit, that's a lot of people here. I was actually not expecting so many people to come to a security talk. So yeah, the name of the talk is Slaying Bugs and Improving Software Security Through Fuzz Testing. So here's a quick introduction about myself. My name is Julio. After such warm introduction, but still, I think it's important to say my name again. Julio. I work as Director of Professional Services at Blaze Information Security, and I'm based here in Krakow, believe it or not. And this talk, it aims to be a gentle introduction about fuzzing to software testers and how it can be used to discover security issues and improve the robustness and security of your code. So now let's move on to the agenda. So we started here by doing a quick introduction about fuzz testing, and then we move on to talk about the main types of fuzzer, also mention some of the popular tools that you can use to apply fuzz testing to your own programs. We're going to speak later about a few activities related to pre- and post-fuzzing, also how to integrate this with your DevSecOps pipeline, and finally conclude the talk. So now, quick introduction to fuzz testing. So basically, fuzzing, it is about sending inputs automatically to a software and monitor its behavior. But this is in a way that you software testing people call negative testing. So the idea is to find inputs that cause unexpected behaviors, such as crashes, hangs, memory leaks, or, for example, access violations in memory. Most of the early research on this topic was done by Professor Barton Miller in 1988 from the University of Wisconsin. So the story was that he was working remotely. Well, back then, apparently people already work at home office, over a dial-up connection, like modem, for those of you old enough to remember. And it was a stormy night that created a lot of noise in the line. And then most of the comments that he was typing, so many of them were being corrupted. And because of that, the programs, when reacting to that, to those corrupted data, were crashing. And then he had the idea that, maybe I should study this in a more formal way. And so, yeah, it's been around 30 years or so that this became actually a kind of a formal topic of study. And brief introduction about fuzzing again. It works against software with or without source code. With source code, we can actually use a few things such as instrumentation, for example, that it will guide our further. We're going to talk about this a bit later. But also it works perfectly fine with software, in software without source code, closed source and just binaries, for example. It's a very important element for a robust SDLC. So SDLC stands for Security Development Lifecycle. Microsoft came up with this, actually they are the ones that have the most robust one, came up with this almost some 20 years later. And if you see fuzzing is one of the elements of this security development lifecycle. And as an anecdote, Microsoft, for the release of Windows Vista, I know, like, well, I didn't like Windows Vista either, but Windows Vista was, like, it had like a significant security improvement over the previous versions of Windows that were released, because Microsoft did like a very strong like security push towards Windows Vista, and they used fuzzing a lot, like very extensively in the development lifecycle. So over 15 months, if I'm not mistaken, they did fuzzing in many different parsers and programs in Windows Vista, and they managed to like find and fix prior release over 300 security bugs in that operating system. And because of that, like, well, it's definitely battle tested, and it can really discover critical bugs. So, but there's a catch here. So, like, again, like, it works by sending valid data to a program, but the catch is if data is too valid, nothing will actually happen. So, you will just get the data that you created, and it will process it nicely and give you like an output. If the data is too invalid, something will actually, I mean, most likely nothing will happen. It will just be rejected straight away as a completely non-conformant data. And, well, I don't know how to handle this, and just stop. So the idea here is like to find this sweet spot of generating data that's not too valid, but also not too invalid, but still enough to be processed as deep as possible in the program state, and hopefully discover some actual security problems, or even like robustness issues as well. And of course, it observes the program for like how it's behaving when it's processing that particular input for hangs, crashes, and other unusual behavior. So here we have like a basic fuzzing cycle. So let's actually use the mutation engine here, like, I mean, the mutation-based fuzzing as an example. You use like a seed file, like a valid input. Let's say we are fuzzing like a PDF reader or like a PDF parser. So we're gonna get like a valid PDF file, and we're gonna apply some mutations to it, and we're gonna create this mangled data, and then send this fuzzed input to the program under test, let's say Adobe Reader or any other PDF parser or reader that you're trying to fuzz. And this will be in around like some sort of debugger or monitor that will see how it's behaving when processing that, that particular input. And if this input actually causes something interesting, we just save that crashing input for later triaging to see what actually is going on here. Now let's speak about the main types of fuzzing. So like mutation-based is like a very popular one. It's probably the easiest one to get the ball rolling. So it requires like a set of seeds, which is like known good inputs. For example, if you want to fuzz like an MP3 parser, get like a bunch of MP3 files as your seed. And it just mangles the data accordingly to like a predefined set of mutations. So like we're gonna talk about later what can be applied, for example, as mutations. And generation-based, so it will be based on a grammar and a format, like some sort of expected input. And these test cases, they are created from scratch. Like, for example, if the data that let's say you're trying to fuzz TCP IP stack. So we all know that TCP packets, for example, like after you create the packet and so on, it creates a checksum of that particular packet and sends to like, well, down the wire. And then this will get processed, but like usually the first thing you would do, like in the other end, will be to check if the checksum is correct. So if you just mutated the data, for example, like without taking into consideration checksum, it would just be straight away invalid. Whereas in this case here, like in the generation-based fuzzer, we can actually fix all these problems related to checksums, integrated checks, and and so on. So now it's speaking about like some input awareness of fuzzing. There is like a few like different type of input awareness here. First of all, like dump fuzzing. So the fuzzer knows absolutely nothing about the program it's been testing, and also the input that is just mutating. It's just going to apply random mutations or generations to it. So let's say it's just at random flipping bits or at random deleting data from the input seed, like depending on whatever heuristics it's going to use. There's obvious disadvantage here, like some shallow test cases and less effective results. As I just mentioned before, the related to checksums, for example, like it's just like an example here. The dump fuzzer will probably never really, like when it's corrupting the data, whenever it's gonna do whatever checks afterwards, like integrity checks, we just say like, oh no, this is too invalid. But it doesn't mean that this is useless. In fact, I personally have used this like to discover like some problems. For example, in VLC, which is like a popular, popular video player, for example. So like dump fuzzing actually can give like some fairly decent results, but depending on what you're gonna fuzz, it may not give. Now format aware, like fuzzing, so it does like generation of inputs based on a predefined specification, and the test cases, they likely to be processed. Like, so it means that you're gonna get better results, means that your test cases are less likely to be rejected right off the bat, and it means that you can traverse more code, therefore like having like a larger code coverage and having like a greater possibility to actually discover problems. In-memory fuzzing. So this is actually not super popular, I would say, at least. Yeah, not all fuzzers do this. So in-memory fuzzing is usually when you want to target a specific function for fuzzing. So it's a bit tricky. Like if you have your function, and before the function, you set a breakpoint, and right after the function, you set another breakpoint. And this will be considered the one, like the last one is the restore breakpoint, and the first one is the snapshot breakpoint. So whenever you have your input coming, whenever it hits that particular breakpoint, the snapshot one, you take like literally a snapshot of the entire context of the program, whether it's registers, I don't know, thread environment blocks, and other information about state, maybe of heap and stack, and so on. And then you take that snapshot, you do whatever magic you have to do to, say, mutate the input, give it to the function, let it just run. Whenever it hits the other breakpoint again, you would do the restore of the state. So it's essentially you just like looping around it until you hopefully gonna find something interesting. There is like evolutionary that is also like usually covered guide fuzzing. It generates new inputs based on feedback from what's being fuzzed. So like this actually became very popular with AFL that we're gonna see a bit later. So the inputs, they're generated by genetic algorithms, and then you have something that will monitor the program, also not only for crashes and so on, but also the states of like code paths that it has traveled to or code coverage, and then keep talking back to the test case generator, say, hey, like this input that you just created gave me, say, 10 different code paths. These are the code paths. Can you just keep improving? And then, okay, now this one gave me like 15. So cool, like we are progressing here. So it used genetic algorithms to leverage, and also like this coverage tracing and so on, to traverse more and more and eventually explore as much as we can from the program like space when it comes to to parsing like data. Let's move on. So what can be fuzzed? Well, pretty much everything, like from web applications, browsers, image editors, libraries, APIs, well, you name it. Kernel system calls, network stacks, server-side applications, like pretty much everything that has a parser, pretty much everything that gets input from somewhere and does something about it, it can and probably should be fuzzed. And now let's speak briefly about, actually let's get to see some, like with our own eyes, some fuzzing. So there is something called glitch art. I don't know if like some of you have heard about it, but glitch art is essentially, there is like some huge communities online of people that get like images and they distort those images on purpose, like by injecting like faults, like mutations and so on in these images and also videos to create like these like aesthetics, like these visual aesthetics that sometimes actually very pleasant to the eye. I actually like to see some glitch art. And even here in Krakow, there was like some 2 years ago, there was kind of a small exhibition on glitch art. So it's something that's actually pretty interesting. And I think it illustrates very well the concept of fuzzing. So let's see here an example to glitch Krakow Rynek. So let's just see now. So as you can see here, some images are more broken than others. And like these are all glitched images. So because sometimes, for example, the mutations that I did, it hit, like say, it mutated some important part of the particular file. Like say, for example, these are the bits that will control the pixel density, or will control some information about the colors, about the height and width, or something like this. And then sometimes we can actually, sometimes we can hit some of particular like mutations that will hit like cause some weird, unexpected behavior, which is not the case here. And if you see here, I hope you can read, some of them it says like no loader for this file format. So it means that some images that were glitched, so they were fuzzed too much, like to the point that this was rejected straight away by the parser, and it was not even rendered to us when presenting this. So you can see like here a few other mutations. So actually I'm not sure if this is big enough. I hope that you can still read something. If you see here, there's like a simple example like hello test dive. And then there is one mutation here, that this mutation is just swapped the string, for example. And there was another mutation here that did some, at random, it got the string, saw like its size, and at randomly, it just applied some bit flips. So I think this is like just like a nice way to put it, so we can actually visualize the process of fuzzing. Another one that we can have here, like generational demo. For example, this is like a very, very super simple example of a potential like fuzzer for an FTP server. So if you see here, we have like the user pass and then the command and then some but like some generations of using some inputs that are usually known to cause troubles. But I think it's very important to state here that if you see here, it knows more or less how to speak with the protocol that it's trying to test from, like to find actual bugs in it. Presentation, okay. So there's like different mutation strategies and heuristics. I just wanted to briefly touch them. We can like byte flipping. This is actually one of like a super common one, and believe it or not, it actually finds bugs. Like, as I say, like again the simple example that I mentioned before about VLC. It was just using this type of mutations that ended up finding problems. There's like the addition of these corner case inputs that things are known for causing trouble, like negative numbers, very long strings. I'm sure that you, as doing software testing, you are familiar with this. Deletion of random portions of data, swapping things around, and like many more. There's like a lot more clever ways to do that. Now speaking about some popular tools, mutational based like ZSUF used to be like a popular one. Actually, I think it's lost popularity lately because of Radamza. It's a very good test case generator, and mutator as well. Like there is also AFL, honk fuzz, WinAFL for mutation-based and coverage-guided fuzzers. libfuzzer for in-memory fuzzing. libfuzzer has a bit like a steep learning curve on how to use it, but it definitely gives like some pretty good results. Pitch and BooFuzz, a generation of fuzzers, also create your own. But now let's speak about like some not popular tools, and I'm actually not making this up. This actually happened. So some time ago, like I think some 2 years ago, I was on a call over Skype for Business, and then the call finished, and I just went to the bathroom. I actually left my computer unlocked, which doesn't really happen that often. I was working from home this day, and then when I come back, here is my cat sitting on the keyboard with Skype for Business crashed. So I don't know what kind of input the cat did by randomly walking the keyboard, but it indeed crashed Skype for Business. And I think that's like a best example of fuzzing that you can actually have like in real life. So my cat actually found something that I could probably never find by typing on the keyboard. Now a few words on code coverage. So this is like it's a way like some metrics for fuzzing as well. Like obviously finding bugs is one of them, but the quality of the test cases that we generate that traverse more code is also one of them. And there are like different ways to achieve code coverage with fuzzing. Like compile time instrumentation, this is what AFL does. So essentially, you use like a wrapper for the compiler, and it will add instrumentation when you actually compiling the code, which is like a good thing. But then you need source code for that. But for binary, you can either do as well like binary emulation, set breakpoints in every basic block, which is the old school way to do it. It's slow, it works, not so effective, but I think it's very easy to visualize, and that we're going to see in the next slide. Also, you can use tools like Pin or DynamoRio, for example, even like Valgrind, like the old one as well, to do like the using dynamic binary instrumentation. Certain breakpoints example. So like if you, I don't know if anybody here has done reverse engineering of a software, but this is like a disassembled version of a program, and it's called like so-called basic blocks. So like the program gets, say, divided into these basic blocks. And one of the ways to count code coverage for fuzzing is that you set breakpoints in the very beginning of each and every basic block in the program, and then you give it that input, and then whenever, like, say, oh, this input hit 10 breakpoints, therefore, like, it hit 10 basic blocks, so this is like how you count coverage. Again, this is a pretty old school and not really the most effective way to do it. Like, you have much better ways to achieve that, but I think this is like a very easy way to visualize, so this is why I decided to have it on these slides. Now, like a few activities on pre and post fuzzing. So, like, first of all, is like corpus. So corpus, like, especially for mutation-based fuzzing, we have a valid set of samples for a particular file format or protocol. And these valid cases, they will be mutated to create more forward inputs, as we have seen earlier. And ideally, we would like to have a diverse corpus that will exercise different paths. Like, for example, you want to fuzz, like, again, like a PDF file. You have this PDF file here, and this PDF file may have like a coverage of, let's say, 100 basic blocks, whereas this other one with different characteristics or with more features and so on, I'll say like a different way to render an image and or a different type of image to be rendering, will get like another parser or something in the reader, will have more basic blocks. So it's important to have like something that's more diverse as possible. But then again, there's a problem that many of them will hit the same code paths, and that's what we do. We do corpus minimization. The idea is to find the minimal set that has like a similar coverage. So sometimes you have like 10,000 PDF files that you want to fuzz, and you can reduce these all to, say, only 500 of them because they are equivalent when it comes to, from a coverage point of view. And also reduce the file to the minimum size as possible, but let's still yield the same coverage, because it will definitely speed up your fuzzing process because, well, for example, a 1 megabyte file will take a bit longer to load in memory when you're making your program use that an input if you compare this to a file that's only like 50 kilobytes, for example. Another thing that's probably also like mentioned is like test harness. So in many cases, the fuzzer is generating payloads in a way that you, like, I mean, that whatever application you want to fuzz doesn't really understand. So you have to create something to bridge this gap. And this is, like, that's why we use a test harness. Writing a harness sometimes can be a pain, but I would like to show like a super simple example of one here. Yeah, it's probably not the best to see, but like this is like a simple like a program that I created. Like it works kind of as a library. And then if you can see here, there's like some straight up like buffer overflows and some form of string problems and a few other issues with like integer manipulation here that will cause this allocation here, not this allocation, but like this copy to also fail. But how to approach that if this is like, for example, a library, but then the fuzzer used for this purpose is AFL. AFL will not really be able to send the data in that particular way. So I had to create a harness. I know how to quit VI, by the way. So yeah, so this harness that I had to create some code to bridge this gap. So it will get like whatever the fuzzer is outputting, pack it into a struct, for example, because it was the way that the program was expecting to process that, and then call it the function with whatever fuzzy data that the fuzzer and test case generator spit out. Also, like a few activities on post-fuzzing. So there is also crash test minimization. So this is the act of reducing your test case to the smallest possible size in a way that still triggers the bug. So like later for triaging, it will be very important to, like, if you have like a file that's like 5 megabytes, well, there's a lot of trash there and so on. And the idea is to reduce this as much as possible so we can actually debug it later. Now, like a few words just like on DevSecOps integration. Fuzzing can, and in my opinion it really should, be integrated as part of any security-oriented pipeline. There are like a few existing initiatives, like Google SS Fuzz, for example, does continuous fuzzing in some Google Cloud and some like a lot of resources of some open source software like FuzzBuzz, FuzzitDev, and like some other initiatives that makes things easier to put fuzzing into your pipeline, or you can actually roll out your own. As we saw before, like Microsoft, for example, like even like 20 years earlier, this whole concept of DevOps actually didn't really exist, but they were already kind of, they knew that they needed something in the software development process, and this is what they did, and then they squashed like a bunch of bugs in Vista, for example. Now like a quick demo as well. So, let's use new Jenkins. So I'm not a specialist in Jenkins or anything, so I'm gonna apologize for any, like any bastardization that I may have done here in creating this. So it was just like a super quick like config that I did. It was actually, oh, I cannot see it here. So just a second. All right, so what I did here is like in the build process, like it's getting from a Git, and then it's doing some stuff like it's compiling the way that, for example, my fuzzer wants, like with all the instrumentations and everything. And after that, after the program has been built, I have like a sleep 30 seconds that it keeps, like it kicks off the fuzzer and it keeps checking the directory of the output to see if it actually something happened. If there is some bug, for example, or anything that has crashed, it just fails the build. So let's see. this fuzzing run happening. Okay, build now. So yeah, the build is happening. Let's see the console output. So yeah, well, it already found one unique crash. So I mean, obviously, it was a program already built for crashing. So yeah, it's gonna be there like in some 30 seconds. It will just fail to say like, hey, this build has it's not robust enough or it's not secure enough, and fails the build entirely. Obviously, you can come up with your own criteria to fail the build. You can use some programs, for example, to do some automatic crashing triage to see if this is actually like a security problem first. And then if it's a security problem, it just fails the build. Or you can use whatever criteria that you want. So if you can see here, like bug found, failed the build, and everything was aborted. And see here, yeah, the build has failed. So now we're coming to the end of the talk. So let's just wrap up the talk now. Fuzzing, it can be very effective, very useful. This has been like a tried and tested way to find robustness issues and, most importantly, security problems in different software out there. And the entry-level bar for fuzzing, it has decreased considerably in the past couple of years, especially with the creation of like some super easy-to-use fuzzers such as Radamza or AFL. So I think this leaves for very little excuse not to have it in your tool set for software testing, and adding it into your pipeline will definitely improve like the robustness and security of your software in exchange for a couple of CPU cycles that I'm sure you can spare. There's like some useful references for the talk, and now it's time for questions. So thank you very much.
And now let's have some fuzz applause. Julia Fort. And I think, yes, we're now ready for questions. So could we have the questions on the screen, please? Right, question number 1 with 19 votes. So will testers be replaced by cats in the future?
My answer is I hope so. That would be great, actually, if the whole audience were cats. That would be really nice.
Okay, Grzegorz is a winner of the popularity. Yes, so that was the question, and we've already answered that, unless you want to... Okay, then, question number 2. What kind of software do you think is worth testing using fuzzing?
Well, pretty much everything, really, especially if you want to find like security problems. Like, really, anything that has a parser is worth testing, either whether the software that you're developing in-house or something like, actually, I think open source software. It would be good if you want to contribute to actually finding bugs and squashing them in open source software. Like, I think open source software really needs help, especially like in terms of like manpower. That's what I'm trying to say, not because software is bad.
Okay, next question, please. And the question is, could you explain the difference between mutuation testing and fuzz testing from your point of view?
So I think like I don't know much about software testing as much as you guys do, for sure. But mutation testing and fuzz testing, like from a mutation point of view, it looks pretty much the same. Like I think what differs is probably the objective. Like in my case, like I just want to find bugs that I can actually exploit from a security point of view and take advantage of them. Whereas when you're doing this like mutation testing for like software testing per se, it's like your intention is actually to fix those bugs. But yeah, I think it's mostly, but it's very, very similar like it's more like the intention. I think in the end, that's a bit different.
Next question, please. Have you ever hacked into something? I'm not going to read that word.
Can we skip?
Yes, of course, it had only 9 votes.
Well, this is being streamed, so.
Yes, let's not incriminate ourselves. Next question, with 8 votes, can the fuzz testing be used for performance tests?
Really, I don't know. I never really saw this being applied for this purpose. Maybe it's something worth checking, worth investigating, but I don't think I have a good answer for that one, I'm afraid.
Okay, still time for some more questions. You do realize that Skype crashes so often that the probability of your crash being caused by a cat is very low.
Yes, that may be true, but I like to think that my cat's super smart and he knows what he's doing.
Okay, next question, please. I'm sure there are a lot more about cats. Fuzz testing generates a lot of test cases, but also test results. How to handle or monitor those results effectively?
Well, that's the catch. So there are like many fuzz like frameworks that already has all the toolings around this. So you can either create your own stuff or you can piggyback on already existing frameworks and modify them for your purposes. And I think that's what I would do. I'm not sure if I would create anything right like from scratch unless it was really necessary. But there's like plenty of frameworks out there that you can probably just modify them in order to serve your purposes.
And one more question. Let's have the final question. In your opinion, what is the one best practice worth to be highlighted in security testing?
So I think that especially recently, this whole DevSecOps thing is been gaining a lot of momentum. So I think that doing security testing, even if it's automated, in a continuous fashion, it's one very, very good practice to highlight. And having this really embedded in your software development lifecycle, it's probably the way to go. Like, because in many cases, sometimes people just want to do security testing only in the end, after everything has been built, and then it will cause a lot more problems and will cost a lot more to actually fix those issues than if they were caught in the very beginning of the development process.
Thank you. And a question from me, if you don't mind, but it's actually the question for the audience. Now, the audience, what do you call a quality assurance technique used to discover coding errors and security loopholes in software, operating systems, or networks? I'll try again. It's a really easy question. What do you call a quality assurance technique used to discover coding errors and security loopholes in software, operating systems, or networks? Close the cats is very close. More technical term. Okay, I'll make it easy for you. It's called fuzz testing or fuzzing. And this word has been just announced, a new Nokia word, and it's been introduced to us by one and only Julio Fort.
Thank you.